I'd like to welcome all of you to the 44th Annual Electrical and Computer Engineering Senior Project Presentations. For those of you that have not attended one of these before, you should have two handouts. One is a list of the presenters in order, and the second column is the title of their presentation. At least as important is the second sheet, which is an evaluation form. Please make sure you put your name on it and be sure to fill in the evaluations. For the presenters, first of all, I want to congratulate the senior class on being here and getting here today. I think you guys deserve a nice little round of applause. And the day is almost over. Okay. I just want to remind you to pay it. We do have the laptop here. You need to, besides glancing at the audience, sometimes the remote, let's say, skips a beat. You should not feel at all uncomfortable, but it's just saying excuse me and going and backing up or forwarding to the appropriate slide if you need to do it manually. Please remember to repeat questions into the microphone. We are videotaping this. I will be making a DVD of this so you can have it forever. And one other thing, I will be taking a picture of you. Okay, I will try to do it before you start. Yes, I will. I'll only take one. So you don't have to look at me so you don't get the little bright spot in your eyes. Anyway, I want to welcome the faculty and students. Also visitor Professor Haddad from STCC. Thank you for showing up. And the first presenter, oh, by the way, so the format is after you're done in answering questions, you will introduce the name of the next presenter. Okay, you don't have to repeat the project title. And our first, unless there's any questions, our first presenter is Matt Joyce. Matt?
Take a picture? Should I smile? What? Okay. Good afternoon, everyone. I'm Matt Joyce, and my project was the design of a graphical user interface monitor for the 8088 processor. My faculty advisor was Dr. Christ. Okay, a little overview. I'll go over the background of the project, my problem statement, my objectives, the solution, the system constraints, the procedure I took to complete the project, my programming language selection, my testing, and then my conclusions. In CPE 360, the students create this board right here. You have the 8088 processor, the EEPROM, which you run programs out of, and then a RAM, which you can store data on, and of course some blinking LEDs. The communication background. Right now we use HyperTerminal on the PC to send commands to the monitor running in the EEPROM. The EEPROM then executes those commands and sends the result back to the computer. This is all text-based. For software background, the PC, as I said, the PC communicates through the serial port using HyperTerminal. Two students have worked on this so far. Richard Cordone in 2003 created the original monitor, and Matthew Bosquet in 2005, last year, made some additions to it. Also, Matthew Barker created a C++ program that runs on the PC and allows the student to download programs into RAM and then execute them. My objective was to add a graphical user interface to all of these functions. I had to include the functions of the past projects, which was the serial download, the execution of programs from RAM, and the single-step capabilities in the newest monitor. This is the problem. Right now we write text, that's pretty shaky, text right here, and it sends it to the EEPROM and then returns more text. This monitoring procedure is text-based and tedious. The slowest baud rate of 2400 is capable of sending 266 characters per second, but one read command takes 30 characters, therefore you can read approximately 9 address locations per second. It takes the user longer to type one read of an address, so typing in you can read one address in more than 1 second when there's a capability to read at least 9 characters per second. So the speed of the current system is all dependent on the user input, which I want to eliminate. And here's a pretty picture of the solution in action. The user now goes to a black screen, I guess. What's playing here? We'll skip that. It was a picture. Alright, so the solution explained. The graphical interface is used to automate the transmission of commands to the EEPROM. So instead of typing a command, my program sends those commands a lot faster than a user could input it. It integrates the download functionality from previous projects, and it also creates text files of any reads from RAM or EEPROM. Some of my system constraints was sustainability. If there are changes made to the board, there's going to need to be changes to the software, which brings me to the next problem, is the programming language I chose. Students currently aren't familiar with the language, so if a student was to take on this project in the future, they would have to learn it. But I learned it, so I think most other CPEs will be capable of it. The system needed to be user-friendly. If it's no more useful than the text-based monitor, nobody's going to want to use it. And also originally I had a time constraint because I only had 4 months to create this, and luckily that wasn't too much of a problem. The procedure I took was I first researched past monitor projects to ensure I could include all of those. I then analyzed several programming languages. I then researched serial communication and graphical interfaces with Windows XP because that is the system running in the CPE lab where the monitoring takes place. I then wrote the code in the selected language, and I tested the code and reported the results. The programming language selection. It's a combination of Visual Basic, PHP, and C++. The main advantage of this is that it's actually web-based, so you could monitor your board from California, China, anywhere. And we don't really need that for CPU 360 because we're going to be right on the computer, but for future endeavors, it might be a good thing. The speed far surpasses the user input. The options are also much greater with this. You can read address ranges instead of just a single address. And then it was tested on all 32-bit Windows systems and works on those, except for in the lab that has the Ghost software. Also the advantage is that it's user-friendly. It's a lot easier to point and click than type. The one disadvantage, as I said, is that the users aren't familiar with PHP, so they're not going to be able to immediately edit it, but it's nothing hard to get used to. It's similar to C++ or C, which we are all comfortable in. Here's a breakdown of the programming languages. Visual Basic was used as a basic frame to load in the PHP language. So when the user clicks the exe on the desktop, the splash screen for Visual Basic appears while the virtual server loads, which will execute the PHP language. Once the server is loaded, the user goes to the welcome screen where they'll enter their user data. Once they're through that, they'll get to this. So this is a little breakdown. As you can see, back here is the Visual Basic frame, which loads the PHP interface much like a website or Internet Explorer loads a website. So the PHP interface is executed on the server and then brought into Visual Basic through the frame. This is a little system flow. When the user gets into the system, they have to set up their connection settings, which is then sent to a global variable. It's userdata.php. This holds all the variables concerning the connection settings and their memory settings. Then go to the welcome screen where they can advance to adjust their settings if they made a mistake. They can go to hardware and test EEPROM, RAM, ADC, LEDs, and then any I/O devices that might be added in the future. And there's also the software section, which allows students to download binary files to RAM and then execute them in the debug section where you can single step the program and run it. Some of my problems encountered. I was going to originally link to bark360.exe, which was a C++ program, which would have saved a lot of time in not having to create my own download system. Unfortunately, the bark360.exe did not correctly close the port upon exit, so my software was unable to access the serial port. So I then had to integrate my own software download system into the interface, which posed the problem of parsing through the bin file to actually extract the instructions. The solution was to create the design in PHP that actually parsed through the bin file and successfully put it to RAM. And here's that, oh, crud. Here's a video of it working. It's pretty nice. So the user browses to their file anywhere it could be located on the floppy drive, the hard drive, or C drive, or even a USB thing. And you upload it, and then you enter the org address you want to be located in RAM, and you download it. The user then gets to see the instructions and the address those instructions are located in, which my software parsed out of the bin file. Alright, for testing, I tested both memory mapped systems and IO mapped systems to ensure both IO setups worked. I tested the download function on multiple baud rates to ensure it worked for everything. And then the software was made available to the current CPE 360 class. Future work. I was originally going to add an integrated development system where you could write your code, compile it, and download it all in one section. Also, I'd like to add support for the Mon51 monitor, which runs on the processor built during solar car projects in the fall. Alright, my conclusions. Fortunately, it works. It includes all functionality from the text-based monitor, and I added the functionality of the integrated file download, the read a bunch of addresses all at once instead of just a single address, and you can save your data to a text file from the reads of EEPROM and RAM. Any questions?
Without further ado, all right. Good afternoon. My name is Kevin Slitch. The title of my project is Design and Fabrication of a Computer-Controlled Microstrip Patch Phased Array Antenna. My faculty advisor is Dr. Burke. Okay, quick overview of my presentation. I'm going to be going through the problem statement, showing you a system diagram. Going to give you a little bit of background on phased array antennas, go through the component design of my system, and then do a complete system evaluation and make some conclusions based on that. And then we're going to open the floor to questions. Okay, my problem statement. What I'm trying to do here is design a corporate fed array of 4 microstrip patch antenna elements that's going to operate at 1.5 gigahertz. And phase shifters and a digital controller will be interfaced to select the appropriate beam position of the antenna. This right here is my system diagram. A user will communicate through the user interface to a PC to the CPE 360 board, which Matt just went over, which I'm going to modify, which controls the antenna feed network powered by an RF generator to the antenna array on the output, selecting the beam position. To give you an idea of what exactly this means, the way phased array antennas work, you take the signal that you want to radiate, goes through a feed network which splits it up into equal magnitude components going to each antenna element. Each antenna element is excited at a progressive phase shift. This one is beta degrees ahead of phase of the previous one, and they're all like that. This angle beta is related to the scan angle of the main beam. So by selecting beta, you can actually point the main radiation of the antenna with respect to broadside or straight out from the antenna. Okay, as far as designing my antenna went, we used a 50 ohm input impedance for each antenna. Used half wavelength element spacing. The antennas were first simulated and tuned in HFSS, which is a electromagnetic simulator. And the scan angles of -25 degrees, -12.5, 0, 12.5, and 25 degrees were chosen for my desired beam positions. The way, after HFSS simulated it, I milled the patch and tuned it so it would resonate at 1.5 gigahertz, the operating frequency of the system. To do so, I had to add a little bit of copper tape here to actually change the physical dimensions because the simulation did not agree exactly with what was produced due to various tolerances and possibly dielectric constant error. So after tuning it with the copper tape and making sure it resonated the appropriate frequency, I milled out the 4 patch array, and they resonated at 1.47 gigahertz, which is just about 1.5% different than what I wanted it to. Phase shifter design to generate the appropriate beta values for my phase shifting network. I employed switched line phase shifters. I've got a picture here of a generic, it's like an N-bit phase shifter, where there's various paths to the output. Switches are used on the input and output to select which path the signal takes. Longer paths put a longer phase delay in the signal that's going through. So that way you can select the appropriate beta. The final design had one with 3 delay arms because I needed 3 different betas. This is a prototype of one of my phase shifters. This delays the signal by 88 degrees. This one does by 43 degrees, and this is what they're referenced to in the center here. I used by Skyworks. This is a gallium arsenide microwave switch, single pole 4th row. I used some 100 picofarad DC blocking capacitors and some 50 ohm high frequency resistors right there. They're really small. These parts are 30 thousandths of an inch wide by 60 thousandths of an inch wide. This was the feed network. For the feed network, I had to design 2 types of power dividers. One up here called the primary divider, and these are secondary power dividers. These just serve to split the power equally going through the branches. So hopefully by the time the signal comes out here, they're all at the same amplitude. This is the completed feed network. You can see all the phase shifters in here. All these wires coming from here are the digital control lines. Each switch requires 2 TTL control lines, VCC and ground. So there were 8 wires coming from each phase shifter, and they were labeled A through F. The computer control was relatively straightforward. This right here is the CPE 360 board. What I did was I took off the analog to digital converter that was on there, used a port on the 82C55, which is a parallel port, 8 bits. Part of that signal went and talked to a GAL, which I wrote a description for, GAL 16V8. And then I made a little LED indicator display just to show which scan angle was chosen. The 8 bits from the output of the GAL came over here and basically connected to each one of these are the phase shifter. Each phase shifter connects here. And the control lines went to the appropriate phase shifter. To evaluate the system, I had to assemble the whole thing. And we actually did this in the back of the electrical engineering lab. This right here is my 4-element array. I have kind of on the edge of a desk a protractor in front of it so I can see what angle that we're at. Using a test antenna that was set in the far field, which is about 50 inches away, and using a thin cable, we attached the test antenna so we could keep it at constant radius and then moved it from all the way off this side all the way around 180 degrees to the other side and took power measurements for the received antenna. So that way where we can find maximum power is where the beam's pointing, basically. There was a lot of error involved in this. What we really need is an anechoic chamber for it. Just in the way we were testing it, there was a lot of error, and then there's a lot of received power that the antenna's picking up that's not for my project. I'm going to go through each one of the scan angles to show you how my results agreed with what was expected. This blue curve here is what HFSS had showed was supposed to be the appropriate beam. You can see that this is a scan angle of minus 25 degrees off of broadside. You can see that the beam agrees very well considering the test setup. Over here, you can see that there's some extra power being received, and that's just ambient power being received. As we scan, we go to minus 12.5. The beam also agrees very well with what was expected. Broadside, you can see right here, it's sticking straight out from the antenna. Moving to 12.5, this was also very good. And then 25 was a little bit off, but that could have to do with more measurement error. Conclusions, all the objectives for my project were completed. The scanning performance worked very well considering the setup that I had, and I built everything by hand. Future senior projects could incorporate this in like a very simple radar system or possibly a communication system. I'd like to acknowledge my advisor, Dr. Burke, for helping me with all this stuff. Advanced Technical Ceramics, Vishay Thin Film, and Skyworks for providing samples. Phil Gorman for ordering all the parts. Pete Bennett for allowing me to use the machine shop. William Frederick Ference III, who spent 4 hours with me measuring radiation patterns. Kevin Gorman, who let me borrow a USB to serial port. That was good. And the entire class of 2006. I'd like to open the floor to any questions. Nick? Okay, the question is, you'd like to see an example of how you might want to use this. For something like a communications network, for example, you could modulate a signal into it using like amplitude modulation. And because the bandwidth, I got like 1.4% bandwidth out of it, so using a low frequency signal, you could modulate that into this guy, transmit it, receive it with another one, and then demodulate it. So you could actually communicate with the high frequency signal. Also with radar, you can look at what gets reflected back, and you could make a determination of how far an object was away from the device. Answer your question? Okay. Any other questions? Phil? Yep. Oh, okay. Working with Phil wants me to mention about working with surface mounts. The devices at 1.5 gigahertz, at very high frequencies, you have to use very, very small devices because the actual lengths of the traces and connectors in there all play a role in how the performance of the system. For this one, I had to use very, very small components, like I mentioned, the resistors and the capacitors, and we had to get special tools, a special soldering iron, and big magnifying glass and stuff. So it was sort of difficult to do the surface mount, but once you got the hang of it, it was all right. And any other questions? Okay. Next presenter is the firefighting robot team.
Is that gonna do it? Okay. It's a good picture. All right. I'm Chris Ballard, and I have with me Mike Zaluki and Chris Dockendorf. We were the firefighting robot team, and our presentation today is entitled The Redesign and Fabrication of an Autonomous Firefighting and Rescue Robot for the Trinity College Competition. And we'd like to thank our advisor, Dr. Northrup, for this project. So I have this. Today, this is the itinerary that we will be talking about. We'll be going over the problem statement for this project and the realistic constraints that were placed upon the robot. And we'll go into some of the design that we went through in terms of components that were reused from last year's robot, components that we actually redesigned, and the software solution we came up with. We'll be going over some of the testing and the results that came from that testing, some future recommendations for next year's teams who may want to continue on with the project, and a conclusion slide. This is the problem statement for the project. We decided to take a robot that was designed from last year's team and redesign it and enter it into the Trinity College competition this year, which was held on April 8th and 9th. And the robot was designed to perform 3 tasks. It had to find and extinguish 2 candles that will be randomly placed in rooms in an arena, either on the 1st or 2nd floor of a 2-story arena. And it had to find and locate a baby and drop a beacon marking its location. The baby will be located on the 2nd floor of the arena. And it had to ascend and descend a 15-degree inclined ramp that would be anywhere from 150 centimeters long to 300 centimeters. And because we entered it into the expert division of the competition, there were a few other constraints we had to go by for our design. The robot had to be able to maneuver across uneven floors, and it had to make its way around random furniture that would be placed in rooms. And it had to be autonomous. It couldn't be tethered or controlled by us once it was started. The robot could only be started upon hearing a 3 to 4 kilohertz tone that would be held for a maximum of 5 seconds. The dimensions of the robot had to fit within a box that was 30 centimeters by 30 by 30 centimeters. And the layout of the arena that the robot would be competing in was not known to the team before the competition. As far as realistic constraints that the robot was placed upon, the robot had to meet constraints for manufacturability and for health and safety, and there were criteria for success that we placed upon each constraint. To pass for manufacturability, the robot, we set a cost ceiling at $1,000. We figured that was a decent level for cost of manufacturing. And we set up a bill of materials for all the components that were put into the robot, and we also described the locations and assembly for actually building the robot. For health and safety, the robot's operation could not be harmful to the public while it was being operated, and different things we had to factor in were sensor choice. There couldn't be any harmful radiation in the sensors we chose. The navigation speeds and maneuverability, the robot couldn't be destructive when it was operating. And the means of candle extinguishing, even though blowing air on a candle would blow it out, that's not a realistic way to put out a fire, so we steered away from that for our extinguishing means. And also, the robot had to successfully find the baby or extinguish at least one of the candles during a 6-minute run. As far as the design, it was completed over a period of 12 weeks. And a number of the components from last year's robot were reused. As far as things that we redesigned ourselves, we redid the sensor system for the robot and completely revamped the code and used a completely different processor. The components that were recycled included things like the chassis and treads, the battery pack, the H-bridge motor controller, the water tank piping system and sprayer nozzle, so the entire extinguishing system. That had to be rebuilt, but the whole design was reused from last year. It had to be repaired. And the encoders and the flame detection array that was used last year. As far as the chassis and treads, they were designed by last year's robot team and milled here in Western New England College. It was a dual tread design with 2 separate drive motors, and it had adjustable positioning for the motors and gears and adjustable tensioning for the treads. I'll bring Doc in.
The battery pack that we ended up using, we used the same one that they used last year. It was a 10-cell battery pack for a total of 12 volts. It lasted for approximately 7.6 amp hours, and to recharge it, it took about 20 minutes. And we had to be careful with the way to recharge it. We had to make sure it was completely discharged, otherwise it has memory problems. All Nikon batteries have memory problems, and if it didn't discharge all the way, when you try to recharge it again, it wouldn't get all the way up to its maximum. And also, if we left the light bulb array, which we used to discharge it, if we left that on there for too long, it would actually change the polarity of the battery, which would pretty much render it useless. So I had to be kind of careful using that. Oh, wrong way. Okay, the H-bridge we used was basically it was a maxi dual H-bridge motor driver kit, and this was basically the circuit that converted the signals from the processor into usable signals that were sent directly from the battery to the motor to drive the motor, each one independently in either direction. And there were 4 possible motor settings, forward, reverse, braking, and neutral. And the outputs could be anywhere between 10 and 40 volts. The water tank, piping system, and nozzle, we used the same parts from last year's robot, but the way they actually built it last year, they made lots of bends in the pipe, which caused it to leak in 3 or 4 different places. Which obviously, leaking water in a electrical system is a bad thing. So we completely decided to redo it. The tank was filled with about 3/4 water and about 1/4 air, so that there was enough room for the pressurized air to actually pump the water out of the tank. And the nozzle on the outside was kept always open, and the solenoid actually switched it between on and off, which was controlled by the microprocessor. The encoders that we used are Agilent HRPG series encoders. They're basically beam breaks for the robot. Anyone who did the solar car project knows what beam break is. Basically, as over 1 revolution, a standard beam break will break the beam once. This is a high resolution form of that, which did it 512 times each resolution. So we knew exactly how far we turned either way. And there were 2 separate outputs for each encoder. Basically, it sends a digital pulse as it turns, and depending on which way it turns, it sends one pulse first or the other pulse first, depending, on if it's going counterclockwise or clockwise. And the flame detection array, which was reused from the 2004 competition, consisted of a series of 5 phototransistors arranged linearly like this. And they were biased differently so that the ones on the outside would detect the candle from further away, and the ones closest to the center would detect it closer and closer away. So you can kind of, the robot would be able to be controlled so that it would like manually dial in to where the flame was, so we can get close to it and put the thing out. The redesigned components that we used for the robot includes the IR distance sensors. We completely redesigned where they were put on the robot and how we used them. The digital UV sensor, this was actually purchased by the 2004 competition, but was not used last year. The sound activation circuit was completely redesigned. We added a front bumper sensor because there were a few problems as we were testing. The robot would just literally run into a wall and stay there, and so we had to come up with a bump sensor so that it didn't do that. And again, we used a completely different processor and totally revamped the code, and the robot layout was completely different than what they used last year. The IR sensors we used were the Sharp GPD12 IR ranging sensors, and it outputs an infrared signal and basically sends out a signal at a certain angle, and as the signal gets reflected off of a surface, it measures the angle that it's reflected and converts that into an analog output voltage between 0 and 3.5 volts. And we used 9 of these to navigate around the hallway and avoid obstacles. The UV sensor we used was the Hamamatsu UVtron R2868, and it came with its own driver circuit. This is a digital ultraviolet sensor, and the output of the sensor is a series of digital pulses. The closer it gets to flame, the quicker the pulses trigger. And this has full 360-degree directivity, so that it can really detect a flame anywhere. So what we had to do was, Chris actually fabricated a very well-designed paper box that we put over all the sides except for the front, so that when there was a flame in the room, we could, know that it was in front of us and go towards it and put the thing out. This is the sound activation circuit that was redesigned. It basically consists of a low pass or a band pass filter right here, and this is an amplification stage. This is a half wave rectifier, so that if the output of this is going to be a sine wave, this band pass cuts off any frequencies below like approximately 3.2 kilohertz and above 3.7, 3.8 kilohertz, somewhere around there. And this will amplify it up a lot. And this will cut off any negative portion, leaving a positive DC value. And this cap right here basically holds, as the sine wave goes to a peak, it'll basically hold that as it slowly discharges through that resistor. And this Zener diode out here is a 5.1 volt Zener, so that it would protect the processor. Anything going over 5 volts will, destroy it. So we don't want that to happen. So that's why that's there. The bump sensor that we used was actually fashioned a couple days before the competition. It was made out of a couple pieces of solid wire right here, and was connected to a push button switch. And the output of this this sensor right here was sent to the Schmidt trigger. And this is the accompanying circuitry for that. Basically just consists of 4.7 kilo ohm resistor. This is the actual triggering of the switch. It's set to the Schmidt trigger.
The processor that we used was an Infineon C167 integrated computer board. Hold on 1 second, excuse me. Alright. On this processor, embedded into the processor, was a 10-bit 16-channel ADC converter. It also had 4 individual pulse width modulated outputs, which is often referred to as the PWM. It also had 32 capture compare interrupt inputs. This is often referred to as the Capcom. The processor also had 32 digital inputs outputs. These can be set to be used as either an input or an output by setting special function registers. The processor also had, on the processor board was also flash and standard RAM. There was also an RS-232 serial interface for communication with our computer. And there was also 16 user accessible LEDs. By user accessible, this just means that they can be written to or read from software. Oops. The software solution for our project. The code was written in C using the Kiel Microvision IDE. What an IDE is it's basically, it lets you write code in C, and then it takes that code from C and converts it to assembly, and then we'll take that assembly code and generate a hex file, which will run off your processor. We used a program called DAVE, which stands for Digital Applications Virtual Engineer, to set up all the special function registers and to do calculations for those special function registers. This is a basic flow diagram of the code that we wrote. Oops. It starts over here at the system power up or reset, and then moves into the initialization phase. In the initialization phase, that's where all the special function registers get set up. Then it moves into the sound activation phase. The sound activation code simply took the output from the sound activation circuitry, actually the output from the Schmidt to that. No, not the Schmidt, sorry. Took the output from the sound activation circuitry, which was an analog signal. It converted that to digital through the ADC, and then compared this value to a threshold value. The basic structure for the code here was a loop which constantly checked that value to make sure, to see if it was above the threshold or not. Once it became above the threshold, it would then take 50 more values, and then it would check to see if 90% of these 50 values were above that threshold. If it was, then it would exit out of this loop. This ensured that ambient noise wouldn't accidentally activate our robot too soon. After the sound activation part, the code, it jumps into a loop here. This is the central loop where most of the stuff happens. Inside this loop, it's constantly checking sensors to meet certain conditions. Also inside this loop is a central controller to keep the robot centered in the hallway. These conditions here checked for things such as if a flame was detected and a certain counter equaled 0. The counters were used so that the program counter wouldn't jump into these sections of code too often. Like it jumps into one of these sections and then jumps out. We don't want it to jump back in. Like say for instance, it detects an opening. We don't want it to immediately detect the opening again right after detecting the opening. And in each of these sections where it jumps off of, it jumps into other sections of code. Like here we have the candle extinguisher code. The candle extinguisher code, basically the robot saw the candle in one of its distance flame sensors and it will try to move the robot close to the candle so that can be extinguished. Then it will extinguish the candle by making small movements to ensure that our stream of water would, would extinguish the candle, because you need a constant stream of water to extinguish a candle. Over here is the obstacle avoidance section of our code. Basically, if there was an obstacle in front of the robot, this code would try to reposition the robot so that it could go around the obstacle. If the robot encountered a wall directly in front of it, it would turn. Over here, this is where it checks for the ramp. Our ramp code, we have some slight difficulties with our ramp code, which I'll get into later. But the way we wanted to set up the code was so that it would drive to the ramp and then go up it, set a flag, and then change the controller so that the controller would now be keeping it straight on the ramp. The robot layout. The 2006 robot was completely taken apart and redesigned. The sprayer, solenoid, and piping rerouted around the right side of the robot. As Doc mentioned before, the piping was poorly done last year and we needed to completely redesign it. The first base, which was where we had our sensors, it was just basically a plexiglass base. It was raised up to allow more room for the water tank. The second base, which was our second floor of sensors, was added for IR ranging sensors and the UV sensor. The encoders were secured tighter along the axle. Last year they did a very poor job of that.
Good afternoon. My name is Brian Gordon, and this is my senior project presentation on design and fabrication of a fuel cell-solar powered car. And my advisor for this project was Dr. Stephen Northrup. I'm just going to have a little overview of my presentation. First, I'm going to talk about the problem statement, and then I'm going to list the objectives I hope to achieve, and I'll talk a little background information on fuel cells. And then I will go over my design procedure for this project. And finally, I will talk about failures and problems that occurred. And then I will have my acknowledge people who helped me. And finally, I will open up the floor for any questions. Problem statement is, as we know, the world is too dependent on fossil fuels, especially with the prices of oil going up, as we all know, recently, real high, about $3 a gallon for gas. And eventually, someday, those supplies will run out, and so there's a need to seek alternative fuels for the future, and especially environmental friendly ones that will not produce dangerous gases and harm the environment. And for this, fuel cells have a promising future. The byproduct of a hydrogen fuel cell is just water, and that's very environmentally friendly. And there's also been, for our solar car project in the fall, there's also been talk of maybe changing it to from solar car to a fuel cell. And I will just investigate and talk about the difference between solar car and fuel cell and cost and compare them. The objectives of this project was to design a fuel cell and solar powered car. The fuel cell will be powered by hydrogen gas. And there will also be a third source added to the project, which will be a battery. And it ended up being a 12-volt battery. And what I had to do, since I had three different sources, a fuel cell, solar, and battery, I had to design a circuit board that could interface all three of them to operate the car. And then I also need to find or build a suitable car frame for the project. And since the solar car just happened, there were plenty of parts and other cars to work off of. And here's a little background information on fuel cells. The fuel cell that I had, operating temperature was anywhere between 30 to 40 degrees C. And obviously it's a chemical reaction between hydrogen and oxygen. From the little animation up here, you can see that hydrogen comes in, it breaks apart, and H+ ions go through the proton exchange membrane, and the electrons travel through the external load. And at the end, oxygen is pumped in, and they recombine back to form hydrogen with oxygen, which forms water. And that's the byproduct of the fuel cell. For this project, I need to design a power sharing system. There were going to be three different sources involved in this system. So there was a design of three circuits. Design of a battery charging circuit, and a circuit to determine when fuel cell operates the car, and then a circuit to determine when the appropriate time for the battery to operate the car, depending on the voltages of each of the three sources. This is a block diagram of my power sharing system. There would be, you have the voltage for the fuel cell and the solar panel coming into this connector, and then you would have the battery connector up there. I had to put a 5-volt regulator on the board to power all the chips that I was using, and the voltage, the power for those chips came from the battery, since the battery will always be consistently about 12 volts or 11 volts, and it won't draw too much, shouldn't draw too much current, so it should always be around to power the chips. The battery, there was a battery charging circuit, which when it would run through, it would go, when the battery dropped below a certain voltage, it would go back to connect back to the battery and recharge it from the fuel cell. And then there was a circuit to determine when the battery runs the car, when the solar panel and fuel cell voltage drop. And finally, there was a circuit to determine when the fuel cell run the car, based on when the solar panel voltage would drop below a certain threshold voltage. And they're all connected to a Schottky diode. So if you had a period of time where there was two voltages kind of going to the same node, the Schottky diode would make sure that there's no damage done to each source. And finally, there's a master on-off switch that would go to the motor. As I said, the chips used were comparator and logic chips, the LM393 and the 74LS flip-flops. The circuits, the LM393 was used to compare the voltages, and there was, when the voltages for each source were dropped below a certain threshold voltage, there was a latched event and followed by a RC timeout to reset the flip-flops. And the LM93 comparator would provide the clock for the flip-flop and to reset it. This is a picture of my battery charging circuit. What would happen is when the input voltage, the VCC was 5 volts, we had ground. V plus was a constant 2.5 volts, which I got from a voltage divider coming from the 5-volt regulator. And V in minus, there was a voltage divider coming from the battery, and once the battery voltage dropped below 2.5 volts, the output would go high, V out 1, which is connected to the clock on the flip-flop. And the two clocks on both sides of the chips are tied together along with both resets on both sides. So that would engage the chip, making Q1 go high and driving the transistor and opening the relay. And then the delay, I had to get a delay in the circuit that would prevent the relay from flipping instantaneously and burning itself out. So for this involved just a simple resistor and a capacitor. And this voltage would slowly charge up and time was based on what you chose for your resistor and capacitor values. This would slowly charge up, and when that voltage was greater than, when VN2 was finally greater than VN2 plus, the output would go low and make it reset go low, and then changing Q1 to go low again and closing the relay. And now my comparison of fuel cell and the solar panel. Solar panel, which we already have, they're around $300. For the fuel cell system for this whole project, it was about $1,700. The fuel cell itself was over $1,100. I had to purchase a hydrogen tank, which was $170, and the regulator was about $400. Luckily, those were fuel cell was purchased by an outside professor, and the regulator was given to me by another professor. But testing it, the fuel cell was rated for 25 watts, but I only tested and got 16 watts of power out of it. And the solar panel got 25 watts. The entire fuel cell system weighed close to 5 pounds, about 4.9, although the fuel cell itself was really tiny, only weighed less than half a pound. And the solar panel weight was 10.6. So the watts to pound ratio is better for the fuel cell. However, the dollar to watt is extremely better for a solar panel as of now because it's much more expensive. And next slide here is the graph, the power curve of the fuel cell and the solar panel. As you can see, about 1.6 amps or so, that's when we get the max power out of the fuel cell. And for the solar panel, it happened around 2 amps or so, or a little before 2 amps. Now, some failures and problems occurred. Originally, the plan was to use a methanol cell, but that was not available, and instead a hydrogen fuel cell was sent to us. This led to changes in safety plans because instead of using methanol, we were going to have to purchase hydrogen gas, and it's not the safest chemical to work with. And for testing the fuel cell, when me and Dr. North once decided to test it, we noticed that the voltage at first was, voltage and current were both extremely low. And looking at the owner's manual, it said you had to purge it every minute. So we had, on the the fuel cell had two inlets and outlets. You had one side inlet, and one side outlet. The hydrogen was pumped in one side. The other side was sealed off. So what we had to do, we had to temporarily open the other end, close it off again, and then it would run for a minute and give us about 12 volts. And then after about a minute, you would notice the voltage and current both dying down. So you had to do that every minute or so. And because of some delays in getting the fuel cell, the project was not fully completed. There wasn't time to mount everything on the car and test it, because we need to find or build a secure mount for the hydrogen tank, especially. And that leads to my conclusions. Delays are common in the working world. And like I said, I did not receive the fuel cell until March 8th, and this severely delayed working and building on this project. However, my circuit board did work properly. The power sharing system was a success. And the car frame, I found an old solar car frame and just made some adjustments, had to fix the steering. I had to get a mount manufactured for the solar panel, and that was done. And also, fuel cell was tested. Like I said earlier, periodic purging required for continuous power. And last, my acknowledgement slide, I'd like to acknowledge Pete Bennett, who manufactured the mount for me for the solar panel, Dr. Massey for being gracious and donating the fuel cell, Dr. Northrop for being patient with me and working on this project through the semester, chemistry professor Dr. McCanko, who gave me the regulator to use so I could get hydrogen into the fuel cell, Amanda Zepke, who is the laboratory technician over in Herman, who helped me secure the hydrogen tank onto the regulator, and so we could test it. And then Aaron Westcott for his extensive knowledge of chemistry when I had to calculate or estimate how much hydrogen my fuel cell could use. He was glad to help me figure that out. And finally, the entire 2006 class for having faith in me that I would not have any problems with testing the hydrogen in the labs. Now I'd like to open the floor. Any questions? Dr. Chris? Well, for one thing, we had to store it upstairs in one of the psych labs in a flammable cabinet. It was recommended by Steve Bertoni, who's in charge of safety and chemicals here at school. So I had to keep it up there, and it was just kind of, we had to make sure, always had to go, I asked Phil to come up and get the tank me because I need to have a key, which I got from Mike, the lab technician, and then I had to have a psych professor unlock the door to get to the back room. Any other questions? Dr. Moriarty? The question was, are fuel cells typically that expensive? And yes, I've looked online, and this fuel cell, I remember before Dr. Massey ordered for me, there's this website called fuelcellstore.com, and there's fuel cells on there. This one was $1,156, which I believe, came out of his pocket. And there's other fuel cells that can go thousands, up to like $40,000, depending on the wattage. You can get smaller ones for maybe a couple hundred that do like a watt or two, but yes, they are very expensive because of the metal used to have the reaction. So, but they aren't cheap. Any other questions? I'd like now to turn the floor over to Mike Cervone.
Good afternoon, my name is Mike Cervone, and this afternoon I will be presenting on my senior design project entitled Design and Fabrication of a wireless remote control system for an entertainment scoreboard. My faculty advisors are Dr. John Burke and Dr. Stephen Christ. The next few minutes I'll give you a run through of my project. This will include a problem statement. I'll go through objectives, the basic system diagram, run through of the design of the digital hardware and the analog hardware, how I tested and evaluated the project, conclusions I made, and then open the floor for questions. In general, this project can be described as a design of an integrated digital and analog system. The digital system needs to interface a keypad unit. From that, the analog system is required to modulate and demodulate the digital information and incorporate any filtering that it'll need. It'll also have to be placed on a printed circuit board to must be fabricated for all the surface mount components. And upon success, it will be expanded into a wireless system. The objectives of the project are to successfully implement on programmable logic and demonstrate the analog system. Using VHDL, I expect to read a keypad input, convert it to useful information, and encode it into a bit stream. That will be a 9-bit digital word. I'll have to also model a communication system, most like, I guess similar to RS-232 is what most people in the room are comfortable with. This will also be implemented on the 95108 CPLD board that we have in the lab. The analog system will be placed on a printed circuit board due to the frequency of operation. A level shifter circuit will be the intermediate stage between the digital logic, and the analog system. It'll take the digital logic output and convert that to the required voltages needed for modulation stage. The modulation will be in the form of FSK, which stands for frequency shift key. It's a special form of frequency modulation. This system will then be demodulated back to digital information. This is a basic system diagram. The user keypad is the input to the digital system on the CPLD board. The source information is basically taking the digital information and producing acquired voltage for the modulator, which will output an analog waveform sent through a bandpass filter and then demodulated again. Before designing the digital hardware, the input requirements needed to be set. Basically, the input is standard telephone keypad. From that, 4 device keys were set up for the first 4 inputs. 4 unique inputs basically translate to a 2-bit digital word, and the remaining 8 for the function keys translate to a 3-bit digital word. This is a basic block diagram of the system that needed to be completed before actual design in VHDL. Basically, this is the user interface, being the keypad, and everything else is placed on the CPLD board on the 95108 chip. It starts as a synchronous system is required. Basically, originally it was the system was designed to have a faster clock operate this system so that any baud rate be produced. That also created noise in the system. As the combinational logic in this system is changing, they're complemented with a D flip-flop, and those values are not, they have to reach steady state before you want to read them, and if the right edge is caught here, the wrong value will be loaded. So as a synchronous system, the input to this system basically is constantly reading the column inputs for the rows, and it knows what row it's at based on the Q1, Q0 input here. The Q1, Q0 input, the 2 to 4 decoder basically applies a ground to each row of the keypad intermittently at 50 Hertz. Based on keys being pressed, these 2 values here are inputs to combinational logic for a state machine. They determine the state of the system, and when these values will be loaded into the shift register. The parity logic is input from the shift register, which is all constantly comparing these X, Y, A, B, and C to produce the parity value. Even parity is what the system runs on. And it's not loaded until the very last state. This is the essential layout of the shift register. It's a 9-bit shift register where the most significant bit is the output of the system. This is sent to the level shifter. It's shifted out at the baud rate of 50 Hertz. FSK modulation requires converting digital information to analog information. And the easiest way to do this is through a voltage controlled oscillator. That's this unit here. Basically, the two main components are an inductor and capacitor on the tank and bias pins. The frequency is a function of the inductor and capacitor values. The system is designed for a center frequency of 200 kilohertz, and the varactor diode, which is basically acting as a capacitor. In reverse bias, a varactor diode has capacitor properties. And using a capacitance versus voltage curve in the data sheet, it could determine a nominal capacitance and determine the required inductor. The outputs of this system are a sinusoidal waveform. When the larger the input bias voltage is to the varactor, the smaller the capacitance, therefore the larger the frequency. And vice versa, lower voltage, higher capacitance, lower frequency. The intermediate level shifter circuit is a simple comparator complemented with a non-inverting amplifier. The input is 3.1 volts, which sends it to VEE voltage, and then basically amplified up to 4.6 volts. When the input is a logic 0, it's approximately 2.5 millivolts. It is sent to VCC2, which is then amplified to 5.6 volts. In order to filter this system, I decided to go with a passive filter, third order Chebyshev filter in particular. A passive filter is easier to place on a breadboard. It requires less components than an active RC filter would. It's easier to lay out. However, it requires very accurate components. Otherwise, your bandpass filter doesn't look like a bandpass filter. This is the output of the bandpass filter using the values that I was able to achieve in the lab. There's a small 0.2 dB ripple that you can't see in here. It's minor and isn't a requirement for this system because it's frequency modulation. The amplitude isn't the factor. But as you can see, the bandwidth of this system is the tracking bandwidth of the demodulator, which is 40 kilohertz. Bandwidth is from 180 kilohertz to 220 kilohertz, and the mark and space frequencies being 210 and 190 kilohertz. For demodulation, I chose the XR2211 chip. Basically, this chip has an internal voltage-controlled oscillator of set voltage, and it allows you to design for a free-running frequency, which is basically no input applied. It's the frequency that the chip runs at. There's also several external capacitive and resistive circuit elements applied to the pins to design for filtering, and basically it's like a phase-locked loop system to lock onto the input frequency and provide a logic low or logic high output. And all of these equations are within the data sheet to design for these specific components. The printed circuit board was designed in SolidWorks, and it was milled via the LPKF Protomat C60 machine. The constraints here were to basically just minimize distance between components, minimize trace lengths. Small transmission lines both minimize susceptibility to noise and also reduce the chances of creating a unintentional radiator because it has to meet FCC spec if produced. This is the SolidWorks layout that was input to the CAM machine for the LPKF, and this is the completed circuit with all the circuit components on it. Reactor diode is located up here, the modulator, a DC blocking cap, the passive LC filter are these components, and the demodulator over here. In testing the system, the digital went through several phases. The pre-fit simulation within ModelSim, a post-fit simulation within Project Navigator. These both required a test bench to simulate the hardware. After simulation was successful, it was then implemented on the 95108, and the register was observed via a logic analyzer. As you can see, the automatic high bit that's being read and the start pulse to 0. The device key 2 being hit gives a 2-bit word of 0, 1, which is right here. And function key 7 provides 0, 1, 0, which are these 3 bits here, a parity of 0, and the stop bit. This portion is basically the reset of the system back to initialization state. The register goes back to its original state. In testing the analog system, many simulations were done in SPICE and also laboratory testing. All of the input and outputs of the devices were tested: the modulator, the level shifter, the LC filter, and demodulator. These two plots are the modulator and filter testing. This is the output of the modulator after the DC blocking cap, and it's also the input to the filter. As you can see, there's a high frequency component to the waveform. At 4.06, the frequency was successfully 190.5 kilohertz, and after the filter, all out-of-band frequencies have been removed and remains 190.5 kilohertz. Similarly, it was done for the 210 kilohertz waveforms. In demodulator testing, it was tested both on the printed circuit board and the breadboard. The design was reviewed several times and it was accurate. I achieved the correct free running frequency of 199.4 kilohertz. The problem was that the output remained 0 for any input frequency, and I'm still debugging that chip. The demodulator testing on the breadboard consisted of building the example circuit in the spec sheet and applying an ideal input from the frequency generator. This being this is the FSK waveform input, and the output still is not ideal. It's got about a 100 millivolt DC value and oscillating around 50 millivolt peak square waveform. And there's also the phase shift associated between the VCO locking onto the frequency. For conclusions, the digital system was successful. I can read an input from the keypad, load the correct register values, and shift out the bits. The analog system is partially successful. It does modulate the digital input, and the filtering successfully removes all out-of-band frequencies. The issue still remains that it cannot successfully demodulate to digital values. Basically, if I were to continue this project, or if someone were to continue, I would research issues related to this chip, possibly get a new chip. provided more time, I would also attempt to expand this to a wireless solution using the XR215A demodulator and possibly seeing if that chip removes issues associated with the last one. Acknowledgements, I would like to thank Dr. Burke and Dr. Christ for their time and effort in helping me complete this project. Phil Gorman for ordering all of the parts. Kevin Slitch becoming milling instructor for the senior class. And all of the engineering students. I'd now like to open the floor to any questions. Okay. No further ado, I'd like to ask Andrea Vela to come up and present.
Good afternoon, faculty and students. My name is Andrea Vela, and I am here today to take a couple minutes of your time to present my senior project final presentation entitled Rapid Prototyping Control System using DSpace DS1104 R&D Controller Board. My faculty advisor is Dr. Ranamai. Here is a quick overview of what I will be discussing this afternoon. I will go over the introduction to my senior project, objective, system design, procedure, servo system, PID controller implementation, conclusions, go over some suggestions for future work, acknowledgements, and then open the floor to any questions you may have. The company DSpace is a leading producer of engineering tools for developing and testing control systems. Its systems are used in the automotive industry and also employed in aerospace, drives, and industrial automation. With their single board hardware, everything is in one card. The objective of this project was installing and configuring a single board hardware produced by DSpace and setting up an interfacing package to focus on rapid prototyping, position, and velocity controllers for a servo system. The system will also be used to implement a proportional integral derivative controller. A rapid prototyping system was installed and configured using the DSpace DS1104 R&D controller board. Interfacing software package was done with MATLAB Simulink. It was set up to focus on rapid prototyping, position, and velocity control. A potentiometer was used as a feedback sensor to vary position control, and a tachometer was used as a feedback sensor to vary velocity control. The proportional derivative, and proportional integral derivative controllers were also investigated. This system also required a power operational amplifier to drive the motor. MATLAB Simulink modeled the design, and Simulink expanded MATLAB with a block-oriented graphical interface. There was no writing of code, because when compiled, it generated the C code automatically. After the model was compiled and built, it was then implemented on the DSpace hardware, and the real-time interface generated the required real-time code. After this, the simulation runs completely on hardware, and the control desk, which is the central module of DSpace experiment software, can be used as an interface to model, manipulate, and change any parameters. This is the overall system design used for my project. The PC on the left was used to interface the hardware and software. The controller board fits in the PCI slot, which is located in the back of the PC. It serves as an input and output to the devices being tested. Attached to this board is a ribbon cable, which connects to the the signal breakout box to connect to external devices. This signal breakout box is also known as a connector panel. It provides connections between the controller board and external devices connected to it. The controller board receives the information and commands from the MATLAB Simulink software, and it outputs it through the connector panel to the servo system by the power operational amplifier, and the oscilloscope serves as an input device to view its functionality. This is the procedure to create a model in Simulink. First, you open the Simulink library browser and then select these blocks that you want to use. Drag them over to a blank model window. Then just create the design you want. The design shown in Figure 1 is a model created to operate the servo system, focusing on position control. The set point block subtracts the amplitude -0, which then goes into the gain block, making the voltage of the motor that of whatever the gain is set, in this case 2 times the gain at a period of 2 seconds. It is important in this system not to exceed the gain to more than 4 or 5. The difference can be heard in the motor. The position of the gear goes from 0 to the set value every 2 seconds. This is a servo system used in the project to vary position control. Figure 2 shows the initial position. There's a little black line, I don't know if you can see it, but that's the initial position. And then Figure 3 shows the gear going to its set value down here. After the Simulink model is built and compiled, the position of the gear goes from 0 to the set value every 2 seconds, and the output is seen on the oscilloscope. The control desk was used to set up an experiment modeling the files from Simulink implemented on the oscilloscope. On the oscilloscope, as well as in the control desk. This would allow real-time changing of variables in the model without having to go back and rebuild the Simulink model. All the layouts in Figure 5 were created using virtual instruments provided in the control desk. After a model is built in Simulink and an experiment is created in the control desk, the variables that can be changed in the system will automatically link to the control desk and appear in a tool window. These variables then can be dragged and observed in the layout, like the one shown in Figure 5. In this example, the position gain could either be changed by numerically inputting the gain desired or using something like a slider bar and just change the gain. This would take effect immediately. You would be able to see it in the scope and in the control desk. To implement a PID controller, the first step was to take the model used before to control the servo system and add a PID controller block, which was already provided in Simulink. The gain block from the previous system was deleted, and the PID controller block was added in its place. This also shows the subsystem capability of Simulink. If part of the model is too complex and you don't want so many blocks in one window, you can create a subsystem. And then if you double click on this, you'll get this window, and it has all this fun stuff. After building the model in Simulink, depending on the settings, it outputs the following in the oscilloscope. When the proportional gain is equal to 0.5 and the integral and derivative both at 0, there is a lot of error. As you can see, all this space, that's error. Increasing the integral value will decrease the error and have the curve be close to what you want it to be. Not exact, but it's getting there. If only the proportional gain is increased, this will cause an overshoot seen in Figure 8. Therefore, the derivative would have to be increased and then get a nice pretty figure. In conclusion, the project outcome included successful development of rapid prototyping a control system. This system now has the capability to use real-time interfacing with the control desk. Adding external devices was also successful, and MATLAB Simulink, as well as in the control desk, allows the user to easily control the system being tested. Some suggestions for future work would include the addition of more external hardware, for example, a state space controller. This project focused on a thorough understanding and making sure that the hardware and software system worked with external devices. Now that it does, more hardware can be added and tested. I would like to take this opportunity to thank Dr. Ranamai for all his help and guidance throughout this semester. I would also like to thank Kevin Gorman for helping with the hardware and software installation. And I would also like to thank all the EE and CPE classmates for always being there and willing to help with anything I needed. Now, do you have any questions? Nice. All right. Well, now I would like to introduce Brian Romanek.
All right, hello everyone, I'm Brian Romanek, and my project was the design of a precision real-time clock for an elevator system. My advisor was Dr. Christ, and my corporate sponsor was Otis Elevator Service Center. Before I begin, I'd like to acknowledge a couple of people. First of all, Dr. Christ for his guidance throughout this project. Phil Gorman for helping me find all the parts that I needed for this project. Everyone who brainstormed this project at Otis Elevator Service Center. And Dr. Asif Hassan, who was my contact at Otis and helped me understand exactly how the engineers wanted the project to function. In this project, I'll be talking about the problem statement, the major system components, the importance of the work, the background information, verification of the clock chip for the programmable logic chip, testing, problems encountered, meeting the realistic constraints, the summary of the accomplishments, work to be completed, and then I'll open it up for questions. The problem with this project is that most elevator systems right now don't compensate for the traffic flow of people entering and leaving the building. This creates a problem of overcrowding inside the elevators and an elongated wait time for the elevator. In order to fix these problems, a system was needed that kept track of the current time and sent out an alarm signal to the elevator that forced it to resort to the ground floor as the default operation. This was for the morning. In the afternoon, it depended on the company's interest of where they wanted the elevators to go. The major components of the system included a real-time clock chip that had to be manually adjustable, have a battery backup for at least 30 days, and preferably an embedded crystal. A user panel was needed that had buttons and switches and a display. And finally, a programmable logic circuit to integrate the real-time clock chip and the user panel, as well as keep track of the alarm system. The importance of this work done on this project is important to Otis Elevator Service because they're the ones that are going to be continuing the project, and the work done is going to give them a great head start if they do continue the project. It's also going to be important to any company who has a lot of people entering their building constantly. This is a basic system diagram. The top block here makes up the user panel. The left will be where all the buttons are, 6 buttons, 4 for the alarm and 2 for the increments for the hours and minutes. The right is where the display will be. The programmable logic chip will integrate the clock chip down here. It'll read the time from the clock chip and match it up with the alarms that are input from the user. Then it'll send 2 alarms on and off to the elevator controller. The clock chip that was chosen was the DS14287 real-time clock with NVRAM control. This chip is equipped with an embedded lithium battery and a quartz crystal. The lithium battery is capable of powering the chip when the power is failed, and it also can last for up to 11 years running on its own power. The chip also counts the seconds, minutes, hours, days, months, and years, and compensates for the daylight saving time. The data can be represented, the data being the time and date, can be represented in either binary or BCD, and the hours can be either 12 or 24-hour mode. The chip also offers a wide range of frequency outputs, the highest being 8.192 kilohertz, which was chosen for this project. In order to turn the chip on, a lot of initializations had to be done. The first one, the initializations being the 2 data modes, the square wave frequency. The square wave frequency had to be turned on, and the daylight savings enable had to be turned on. This was done by wiring the chip to a logic board and checking the frequency and contents of the seconds address on an oscilloscope. These are a couple pictures from the oscilloscope. The top signal is the square wave. The bottom 8 signals are the contents of the seconds. The left picture shows the frequency running about at 8.2 kilohertz, which is very good. And the right shows the seconds being counted in BCD. It shows 47. The programmable logic chip is probably the most important component of this project. All the real-time clock chips that I researched were designed to work with a microcontroller. However, my sponsor was interested in using a programmable logic device to reduce the cost and parts count. So the programmable logic chip was to act as a microcontroller to send pulses to the address and data strobes, as well as read and write to the multiplex bus instead of using a computer. The chip was to include a read operation circuit that would read from the clock chip and update the current time. It was to store each alarm time input from the user panel, and it was to display each alarm once the appropriate button was pressed. If no buttons were pressed, it was to display the current time. It also had to increment the alarm time if the increment buttons were being pressed and store the new value back into the alarm registers. And finally, it was to send out on and off arm times to the elevator controller when the alarm times match the current time. This huge circuit is the block diagram of the architecture for the programmable logic chip. Basically, this read circuit right here reads from the clock chip and updates the current time register, which is an internal register. These 4 registers are internal registers to keep the alarm times input from the user. All 5 of these registers then go to this 5-to-1 multiplexer, which chooses one of the registers based on the 4 alarm input buttons. If the current time is chosen, it'll only be displayed. It won't be sent to the next multiplexer. However, if the 4 alarm registers here are chosen, the 16-bit number will be broken up into 2 8-bit numbers for hours and minutes. One of those 8-bit numbers will be chosen in this multiplexer based on the 2 minutes and hours increment buttons. That 8-bit number is then sent to the incrementer down here, which is incremented either by the hours or the minutes incrementer. Then that 8 bits is then restored back into one of the 4 alarm times. The 5 registers are then sent to a combinational logic block, which uses combinational logic to match the current time to the alarm times and sends out 2 signals to the elevator controller. The testing that was done on this project was all done for the implementation of the read operation circuit. It was first simulated in ModelSim and a test bench needed to be created that tested the read operation code. The test bench had to simulate the clock chip, which was very, very challenging. The next simulation was a post-fit simulation in Project Navigator. The difference between the two simulations is that the model sim simulation just tests to see if the code works. The post-fit simulation tests to see if the code will work on the CPLD chip. The last test was to connect the CPLD board to the real-time clock chip and run the program. The LEDs were then viewed on the CPLD board to see if the seconds and minutes were counting the right time and rolling over once they reached 59. This is a picture of the read operation circuit. The left here is a CPLD board. Here are the LEDs counting the time. And this is the real-time clock chip. A couple problems were encountered, the main problem being choosing a clock chip that fit all the requirements. This took a lot longer than expected and slowed down the design of the rest of the project. The other problem was that once I chose a clock chip, it did not seem to be in stock anywhere. And this required me to call Dallas Semiconductors, which is located in Dallas. And it was a hassle because I had to slow down the speed of my speech so they could understand me. A couple realistic constraints that I came up with before the project started. First being cost. The real-time clock chip costs $11.26 per chip, and the CPLD chip costs $22.50. The 7-segment LEDs cost about 59 cents for 5 or more, and the BCD to 7-segment decoder costs only 52 cents for 10 or more. So all these parts were chosen with the cost constraint in mind. The next constraint was user-friendliness, which was met because the system was designed to function as a digital alarm clock, which is extremely easy to use. Durability. The clock chip lasts up to 11 years with power or without power, and it is able to compensate for the power failure with the backup battery. Sustainability. The real-time clock chip is manufactured by Dallas Semiconductors, as I mentioned before, which does not seem to be running out of business anytime soon. Even if they do decide not to distribute this part anymore, I researched a bunch of other clock chips that have a lot of the same features as this clock chip, just maybe a little bit more expensive. Some of the accomplishments for this project: first of all, I did find a clock chip that met all the requirements. I was able to initialize that real-time clock chip. I had to read through a data sheet that was about an inch thick, which is never fun. Then I successfully implemented the read operation with the CPLD board and tested it successfully. And finally, I wrote the architecture for the CPLD board. Work that should be completed in the future, the main one would be the implementation of the architecture that I came up with. This would be the hardest of the three. The next would be to build a user panel. This should be very easy. It could be done with either a breadboard or a perf board and some switches up in the labs. And finally, testing the whole system. Obviously, this wasn't completed since a user panel or the architecture was never implemented. Okay, now I'd like to open up the floor for any questions. Yes, Professor. The question was, what is the purpose of the alarm functions? The purpose of the alarm was to be able to send a signal to the elevator to make it go down to the bottom floor. Without this signal, the elevator is just going to stay at whatever floor. Any other questions?
Is there blue line across? cross that? What's that? Huh? How? FN? What the hell are you talking about? Oh, thanks. If Will's done playing with my presentation, I think I'll start. I'm Matthew Shupak. This is my presentation on the dot matrix LED display for Otis elevators. My faculty advisor was Dr. Christ. My industrial advisor was Dr. Hassan from Otis Elevator Service Center. Quick overview, I'm going to talk about my objectives, the significance of this project. I'll show you a quick system diagram, and then I'll explain the three main components, which are the microcontroller, the display driver, and the display. I'll show you a very basic flow chart of my program. I'll discuss about meeting my constraints, my accomplishments, failures and problems, future work, conclusions, some acknowledgments, and then I'll open the floor for questions. First, my objectives. I needed to build a display component. The component needed to recognize a start signal given by the elevator control module. Once this start signal was received, the component would then begin to receive serial data from the control module. This data would then be parsed to reveal the floor data, and then this data would be sent to LED dot matrix display. The significance of this is that the purpose of the project was to build a larger display that could be visible to people with poor eyesight, to meet Americans with Disabilities Act requirements, and also the dot matrix display allows for finer granulation and character detail, as it uses individual LEDs instead of a bar LED system. Yeah. Here's a system diagram. Up here is the microcontroller portion of the circuit. This includes the microcontroller, the EEPROM, and the USART, which is internal in the microcontroller. The data comes in here from the elevator control module, enters through the USART, and then can be processed by the microcontroller with the use of instructions from the EEPROM. This data is then sent to the MAX6952, which is the display driver, and stored in special digit registers. Then that data is sent to the display where it will be displayed. The 8052 microcontroller, which was a microcontroller also used in the solar car project. It was used for this because it had a built-in USART to simplify circuit design, as there is no need for a chip select for the USART. An EEPROM was used. This was what provided the instructions for the microcontroller, and also allowed for the system to be easily updatable, since all you need to do is burn a new EEPROM. And the microcontroller also possesses a parallel port, which allows for easy control of the MAX6952 driver. The MAX6952 5x7 LED dot matrix display driver was a driver used to control the 3-digit display. The driver provides all alphanumeric characters. It also has 24 programmable characters available in case you don't particularly care for one. The driver also deals with any time multiplexing that would have been needed for the display. And the driver also has its own digit registers, which you can store the characters in and are updated through a serial shift register. The display was a 3-digit, 3-inch by 2-inch dot matrix LED. The display was actually made of two separate 5x7 matrices which were turned horizontally. For the display, columns 0 and 6 were skipped. This was to allow for white space when the 3 digits are placed next to each other. And then rows 2, 3, and rows 5 and 6 were tied together because the two 5x7 displays created a 10x7, and the driver only works with 5x7 displays. So 4 of the rows were tied together, and 1 row was skipped at the end so that it would make 7. Here's a basic flow chart of the program. This only does one character. First, a stack pointer needs to be initialized to some value of the internal RAM of the 8052 microcontroller, and then the driver clock is set low using the parallel port, chip select set low using the parallel port, and then a subroutine is run that sets the configuration register. And then the chip select needs to be set high, then clock needs to be set low, chip select low, then you can write to the digit registers. Then once you set chip select high and clock low, the digit will display. Here's a picture of the finalized board. This part right here is the microcontroller block on that flow diagram. This is the 8052, this is the EEPROM, and that's just a max 233. Over here is the display driver, and each one of these is one of the digits. Here's a picture of the same board just with the lights turned off so you can actually see the letters being displayed. Right here you can see that the row doubled up because those 2 rows are tied together. That was one of the problems encountered. Accomplishments. I was successfully able to receive floor data through the USART. The data was then sent out to the driver, and then the driver displayed the appropriate character, although some characters came out a little off. Failures and problems. I was not able to design the part of the program that needed to check for the start signal. I also didn't have enough time to get into the control of the LED intensity. So as a couple images before showed, those are lit, but you can't see them because of ambient light. Also, rows 2 and 3 and 5 and 6, which were tied together, were even a lower intensity than the other rows because they were sharing the same signal. And another problem encountered was that an occasional inversion of characters would occur. Future work would be to fix these problems, develop the rest of the code to detect the start signal, a testing of the intensity registers to find out what a suitable intensity would be to be viewed at ambient light values. An amplifier should be added to fix the dimming rows 2, 3, 5, and 6. And it's my belief that a flush routine would fix the random inversion of characters, because I believe it's due to a corruption of the digit registers after several digits have been displayed. Meeting my constraints, sustainability. Using the microcontroller with the EEPROM allows for the system to be updated. All you have to do is burn a new EEPROM. Cost, the total single unit cost for just the display and the driver was $22 in quantities of 1,000. Safety, the display is 3 inches by 6 inches total, which should be significantly large enough to be viewed. However, the intensity is too low, so this will need to be addressed. In conclusion, the LED dot matrix provides a higher resolution. The MAX 6952 simplified the project by providing any necessary time multiplexing. The core of the system is functional, and with a few adjustments, the design can be completed. I'd like to thank Dr. Chris, my faculty advisor, Dr. Hassan, my advisor at Otis Elevator Service Center. I'd like to thank Phil for ordering me all my parts, and I'd like to thank Dr. Northrup, who came up with the idea of looking for a driver for the system. Any questions? Yeah.
You said sometimes the characters got inverted. Do you mean like it flipped the letter upside down, or did
No, like
the wrong lights came on?
the wrong lights would come on. So instead of displaying a 7, it would display all the other LEDs around it. Okay. I'd like to introduce Joel Fanouf-Scalise.
How's it going? I'm Joel Fanouf-Scalise, and the title of my project is The Design and Simulation of an Infinite Antenna Array Using a Waveguide Simulator. And my academic advisor on the project was Dr. Burke. An outline of my presentation, begin with a project description, a description of the components used in the project, the theory behind their operation, the design procedure, the test procedure, a comparison of the results between the two, and the limitations and acknowledgements. My problem statement was to design an infinite patch antenna array to operate at 1.75 gigahertz using electromagnetic simulation software, and then to verify the simulated results using a single fabricated antenna element and a waveguide simulator. First off, a single antenna element is not going to operate the same as it would by itself if it were surrounded by other antenna elements. So that's the difficulty in designing an array. An infinite array may seem like not a smart thing to design because it doesn't really exist, but it provides an accurate model of a single element surrounded by a large number of patches. It doesn't have to be infinite. And also the waveguide simulator allows you to use a single element rather than build the entire array and tune it that way, which reduces cost and time. The first component of my project is a patch antenna. It consists of a conducting surface on top of a dielectric. The dielectric I used in my project is FR4, and I excited it using a coaxial cable. Advantages to patch antennas are low weight, low fabrication cost, they're low profile. The thickness of my antenna was approximately 6 hundredths of an inch. And they're also conformable to curved surfaces if you use a flexible dielectric material. Applications would be cell phone antennas, GPS, or you could conform the antenna to the surface of like a missile or something. Disadvantages to patch antennas are they have a very narrow bandwidth. They operate over a range of a few hundred megahertz, low efficiency and low gain. The second component to my project was a waveguide. It's a hollow cavity of conducting material. It's used to transfer electromagnetic energy at microwave frequencies. The advantages are They have lower loss at high frequencies, and they can handle a larger amount of power of comparable transmission lines. Disadvantages are at lower frequencies, the structures can get rather large as the size of the structure is inversely proportional to the frequency. And they're rigid, and special joints are needed to couple the components together. Some of the theory behind the operation of the patch is the simplest model is the transmission line model. The radiated energy is due to the fringing fields at the edges of the patch, which are the curved lines on the bottom picture. These will excite electromagnetic waves broadside to the antenna patch. The next thing is the waveguide theory. Waveguides are used as transmission lines, and you'll get electromagnetic energy propagating down the length of the waveguide. This wave can be farther decomposed into two waves bouncing off the inner walls, 180 degrees out of phase. The angle at which between the walls and the direction of propagation are dependent on the frequency and inner width of the waveguide. Putting these two together, you get a waveguide simulator. The patch antenna will be placed at the opening of the rectangular waveguide. This will force the patch to radiate at the required angle for propagation inside the waveguide, therefore enabling the testing of various scan angles. A scan angle is just the angle from the surface normal at which the patch radiates. The conducting walls will also produce images of the patch simulating a surrounding infinite array, allowing simulation using a single antenna element. The design procedure: first, I constructed 3D model of the patch antenna in the electromagnetic simulation software HFSS. Fine-tuned the parameters, first using the infinite array boundaries at 1.75. I used these parameters and then created the waveguide model in HFSS to compare to the infinite array model. Then finally I constructed the actual waveguide structure and single patch element and tested the performance versus simulated data. The picture on the left shows the model I used for the infinite array. The highlighted areas are the boundary conditions that force the infinite array simulation. The one on the right, the highlighted area, represents perfect electrically conducting walls, which will simulate the walls of the waveguide. That's also a half model split along the symmetry pattern. This is my physical test structure. It's the waveguide with the top removed. The blue cone is an electromagnetic radiation absorbing material. It'll absorb any energy that's propagating down the waveguide so it doesn't reflect back into the antenna, simulating radiation into free space. The next picture is my waveguide with the top on, with the single patch element inside being fed by the coaxial line. I clamped together the waveguide with the clamps, and it worked out well because I could vary the tolerance of the dimensions of the waveguide. Next is a comparison of my results. It has both the computer simulated infinite array and then the waveguide simulations, and then the physical test data. What you're seeing is the scattering parameter, S11, and that's the ratio of the energy transmitted back to the energy first sent out. And the lower the ratio is, the more energy you're going to be radiating into free space. And that's versus frequency. And each frequency corresponds to a given scan angle. And there's that test data versus the scan angle. A comparison of the test data resulted in the two software simulations disagreeing considerably at 6 dB, but this isn't as much of a variance as it seems, because if you looked at regular magnitude, it wouldn't be that much of a variance. This is most likely due to the meshing of the 3D model and the degree of the convergence used. The software breaks down the 3D model into pyramids, tetrahedrons, and variations in that can produce differences in results. The test data and the master slave simulations matched well, and variations are due most likely to the physical patch not being perfectly matched to 1.75 gigahertz, but closer to 1.76, shifting the data slightly. Overall, the test setup was considered successful as the waveguide simulator provided an accurate representation of infinite array at various scan angles. Limitations on the project that I encountered were the simulation software uses matrix algebra to calculate the fields. Calculations become extremely intensive and can take extremely large amounts of time if you want to get an accurate solution. Also, the operation of the patch is extremely sensitive to the physical dimensions. Variations of a few thousandths of an inch can change the operation frequency by hundreds of megahertz. Some acknowledgments on the project is the entire electrical engineering department. Dr. Burke, who helped me with understanding the theory behind the operation and considerations to take in during the project. Kevin Sleech gave me some instructions on the milling machine. Let me use his camera a couple times. Phil, he got me the materials in a quick amount of time. Brian Gordon for letting me use his USB drive. And Pete for machining my waveguide. And now I'd like to take any questions anyone in the audience might have. Yes, Dr. Northrop. Okay, which one? Yeah, that's dB. I didn't necessarily use 6 dB for the bandwidth. That's not an actual representation of the bandwidth of the antenna array. That's changing the scan angles as well. Each, and then in the next slide, each frequency corresponds to a scan angle. So at higher scan angles, you're actually getting worse matching. But I don't typically think that the 6 dB point is taken as the bandwidth of a patch antenna. I think it's usually taken around 15 or 20 dB for good for optimal operation. Well, that's not at normal incidence. That's at a angle. The incoming wave would be approaching the array at an angle. If it was normal to the surface, it'd be around 35, 40 dB. Anything else? All right, thank you, and we'll be taking a 5-minute break, and then Aaron Westcott will be taking the floor.
Joel, your slides. I don't think I can do that. I'll go fast, don't worry. This isn't a senior project. Ooh. Yeah. What? No. Oh, I can go now? Okay, I'm going now, so. Hello? Alright. The title of my project is The Design of a Two-Input Digital Audio Mixer Using Programmable Logic. My advisor for this project is Dr. Northrup. Quick outline of my presentation. I'll first be going through the objectives of the project, then some background information about the hardware topology used, and then into the procedure of both the VHDL and DSK model. Then the evaluation, constraints, conclusion, future work, acknowledgments, and then finally questions. The objectives for the project was to design and fabricate a digital audio mixer using programmable logic, and do the same thing with a DSP microprocessor. Both of these were to be evaluated for speed, versatility, and board space or IC count, and compared. Each of the models includes background. All the models include analog components such as anti-aliasing filters, power for the D to A to D converters, the capture process of actually sampling the sound into the system, mixing block, a filter block, and then generation of the audio output. On the block diagram, you can see the audio inputs going in, some analog filters. There's a capture of the channels and the capture of the potentiometer values to be used as gains. This right here is a mixing process, filter stages, and then finally through a D to A back to the audio output. Okay. First is the VHDL model, analog components made. The first was to create the potentiometer circuit, which would create control voltage between 0 and 5, so you could control the gains of certain processes in the mixer. This is only for on the VHDL model because all the analog components are already included in the hardware on the DSK. Also, I needed to create the power and reference voltage for the A to D and D to A, the input amplification to get it to the right voltage reference on the D to A to D, and anti-aliasing filters, and finally an output filter to cancel out the sample and hold. The first block of VHDL that was needed created was serial communication. Basically, the FPGA doesn't have any debugging capabilities on it, so I can't really see what's going on inside the FPGA. So I created this piece of hardware to send to hyperterminal to tell me what's inside the thing. First starts out with a hex ASCII converter, which will convert a 12-bit input into hex so it can be shifted out. Then it is inputted into a MUX, transmitted through these registers, and out through a shift register to hyperterminal. And also this is all the control logic right here that controls the MUX and these registers. Okay, the next is the ADC interface, which interfaces to the A to D converter. First thing that needs to be done is these control signals to the A to D converters need to be developed using counters and a control logic generator. And then all the inputs are taken in through here into storage banks where I can use them for other models. This interface is also used as the main communication component between all the other VHDL components in the system. So as you can see here, there's a couple output muxes to the filter and the mixing communication areas, and then some filter communication right here. And then also this is the component that outputs to the digital analog converter. In order to implement the mixing stage, a couple of functions were needed because they're not included in the standard as a standard VHDL function. First one is a multiply, and this was implemented basically using a shift and add algorithm, and it was all implemented in combinational logic for speed. The divide was basically a binary long division. It was also implemented in combinational logic for speed, and then we just needed to do test synthesis for the propagation delay. Propagation delay is important because we need to figure out the best clock frequency for the mixing stage, which is right here. This is the mathematical functions used in the mixer. It starts coming from the ADC interface, getting multiplied by gains, adding them together, which is actually the mixing process, into a buffer, divided out, determined by another gain, which was used as the master gain, and then out back to the ADC interface. A counter with a 50 megahertz clock was used to generate the control logic for all of this, and a signal out to the ADC interface to know when to read the signal. Next was the filter stage. I tried to implement a bass and treble filter, used a discrete form 2 IIR filter model, which the process included generation of MATLAB filter coefficients, used sign magnitude math for the process due to the fact that implementing 2 bandpass filters will kill any DC that goes through it, use a discrete form 2 implementation, and generation of control logic. These are the 2 filters that were implemented into the VHDL model. This is the discrete form 2 used. These are the delay blocks, which are multiplied through and then out. This is an example of a second order IIR filter using the discrete form 2 architecture. But there were some problems. The base filter, well, it didn't work. This is due to bit precision on the divide. The divide was so great because of the sampling frequency that the only bit precision out of the divide I had was like 3 or 4 bits, which is pretty much not enough. So this wasn't implemented anyway because space in the FPGA was too much, or it wasn't enough. The treble filter was implemented, but again it didn't work as well as I'd hoped due to bit precision and fixed point math. Fixed point math didn't decrease bit precision for every math function it went through. And I also had some small synthesis problems which I overcame. The DSK model initially had a startup test, which was just to see if the board was working. Used a sine wave generation to see if the board could output a signal, and just learning the components of the IDE. And I did a signal capture test so I could actually input a signal and output, just to see if that worked. The first part was the mixing stage, which is the same model used in the VHDL model. Use the left and right stereo channels for the mixing. The next part was initializing the codec, which is pretty much already done for me using the code. Used a 96 kilohertz sample rate at first, and then I generated the code by using an interrupt during an infinite loop, and every time the ADC has a sample ready, it'll do the processing and then get out of the interrupt. And I also used, because it could not interface with the potentiometers, I used a what's called a .gel file to simulate the potentiometer control in the debugger. And then it was just testing, and it worked. Next part was do the filter stage, and again, same as VHDL model, I used MATLAB to generate the coefficients. Used a discrete form 2 in code, and I used it. I just had to convert the code from the example in a book I used from fixed point to floating point math, and then tested it. Didn't quite work out the first time, but it did work after some simplification. These are the 2 filters. This is the bass and the treble. And then after, on the spectrum analyzer that I used, this is the treble filter here and the bass filter. Okay. The problems with the DSK model was the implementation of filters. At first, using the 96 kilohertz and 3 16th order IIR filters, the processing time for all those filters took too long. So some simplifications were made. You saw the 4th order filters and 2, and then I pulled the sampling frequency down to 48 kilohertz. Another problem was the versatility of the hardware. The only analog I/O in the system was the audio channels. So I couldn't implement the potentiometer control at all except for in debugging. And also I couldn't get away from the computer. I wasn't able to use the flash, and I couldn't do any control with the mixing process, except with the computer, with the .gel files. The evaluation of the two systems, the capture and filter stages were not included because they were vastly different between the two models. Only the mixing stage was included. There's no advantage in the board space because each of the processing only needed one chip. The DSK actually uses this one chip for all the RAM, most of the capture and everything. Speed, each of them, the mixing process only took one sample cycle to process, and then it was sent out to the DAC. Although the processing time for each model, the VHDL model actually was quicker. Versatility, the VHDL model won because it could be connected to many more hardware than the DSK, and it was really easy to change the VHDL model for more hardware. Okay, conclusions. Project was successful. A couple recommendations are to use the FPGA for the capture and mixing stages and use it as DSK for filtering. Another recommendation to increase speed is to use fixed point DSK from Texas Instruments for higher bandwidth. Future work would be to implement floating point math for the VHDL model to get the bit precision to make the filters work, and interface to potentiometers on the DSK model and use the DSK's flash memory so it's not dependent on the computer. I'd like to thank Dr. Northrup for his help on the project, Dr. Christ for his help with VHDL code, Phil for ordering my parts, the OIT staff for providing me with a computer to work from, the Fire Robot team for putting up with all the sine waves coming from my workstation, and all the EE seniors. Any questions? Yes? Probably. But, yes?
Back in the beginning, you had a diagram, and there was a thing called a big loader. What is a big loader?
It's the signal name that I just kind of created off the top of my head. Any other questions? Okay, the next presenter is Kevin Batson.
Hi, I'm Kevin Batson, and my senior project title was Solar Car Improvements, and my advisor was Dr. Stephen Northrup. An outline of my presentation, I'm going to go over problem, objectives, flash, wireless, conclusions, and future work. The problems that my project addressed were transferring data between the solar card board and the computer, and the battery life of the board and the laptop used to acquire the data. The objectives of my project were to improve upon the data transferring procedure and to implement flash memory and wireless capabilities. For flash memory, there were two chips that were implemented to the solar card board, the CAT28F512 and the AM29F010B. The CAT28F512 had 64K of memory, 3 control signals, output enable, chip enable, and write enable. It required a 12-volt programming voltage, and it had a 2-cycle programming operation to unlock the chip to write to memory. It cost $534 per chip. The successes with the CAT were that I was able to get the device and manufacturer signature to to show up. This means that the chip was wired correctly and was talking to me, basically. I was not successful in ever writing anything to the memory. After there was no success with the CAT, I went to the AM29F010B. This had twice as much memory, did not require a 12-volt programming voltage, it just used a standard 5-volt on the board, but had a more complicated unlock cycle. It required 2 more cycles, and it was a bit more expensive. Successes with this chip were the device and manufacturer signatures were acquired, like the CATs. I was able to program to this chip, and I was successfully able to erase the chip. All this stuff was proven with a logic analyzer and compared to the specifications provided by the manufacturer. To program it, it required 4 cycles right here. These 3 were specified by the specifications by the manufacturer. This is the value that I actually wanted to write to memory. These just tell the chip that I'm trying to write to it. So that's why they're the unlock cycles for the chip. To erase, it's the same thing. You have to tell the chip that you're erasing it. But there is no input from me whatsoever. Like these are all provided by the manufacturer. The only way that you would have to change the number down here is if you wanted to erase different sectors of memory. To make the unlock cycles easier for the user to use, I modified the Monitor 51 code. The Monitor 51 is a program that allows the user to interact with the board through hyperterminal. The K and B functions, the K was used to replace the unlock cycle for writing. So the F function that was already in Monitor that writes to RAM is the equivalent of K for flash. To erase the flash, I added a B command. This required no input from the user. You hit B and it would erase the chip. This is a demonstration of the K and B functions being used. D function that's already provided in Monitor just does a dump of certain addresses, and it would work just with the flash because there was no requirement with specifications. So here I'm trying to fill 6000 to 6000 FF with the value of 78 using the K function, and using a dump of 6000 to 60F, it shows that 78 was successfully written. Then after that, I wanted to prove that the B function erased the chip, so I inputted the B, then read the data again, and it shows that the values were FF, which are the values that you get when the chip comes to you. To prove that this chip would work under race code conditions, I altered the race day code so that the A to D channel 0 was pointing to address 6003. That's because the flash was sitting at address 6000 to 8000 on my board. A sine wave was used to be the data that would be taken in during the race. This is the sine wave that was put in. It was going in at approximately 0.3 hertz with a period of 3.33 seconds and amplitude of 5 volts. This is a picture of a graph that was generated from the data that was taken in by flash. The data was exported into Excel and graphed. This point here is at 0.071 seconds. This point is at 3.408 seconds. The period here is 3.337 seconds. And the frequency from this period is 0.3 hertz. So they are approximately the same. The wireless module I chose to implement to the solar card board was the WI.232.DTS module. It was designed for direct RS-232 replacement. It had a small size. It had internal configurable registers which would allow me to change specifications. If the board ever needed to change values and stuff, I could change this with it. And it had master and slave operating modes. Wireless continued. Problems with the wireless. I could not get the solar card board to communicate with it. Without being able to communicate with it, I couldn't successfully program it to the specifications of the board, which would not allow me to test it. Conclusions. Flash memory will improve the data acquisition reliability. The battery life problem has been eliminated. It has increased the storage space of the board, which will allow the users of this board to decrease the sampling time, which will allow more data points, which will give you more accurate data. Future work would be finish implementing wireless, figure out why it wasn't communicating with the board. Future work with the flash would be add a function in Mon 51 to perform the unlock cycles. As of now, I added the K and B functions to perform it in Hyperterminal, but when the users want to save data in like race code looping through, they're going to have to paste in the 4 cycles. It would be easier if they could just have a function call that would do that for them. I also like to modify Mon 51 so that it wasn't reliable, did not need to use regular RAM for MonRAM. As of now, it needs a certain amount of space for the program to run for data pointers and other things that are internal to the Mon 51. And any questions? Dr. Christ.
Were your modifications to the monitor made in such a way that if a year from now somebody comes up with another flash that they want to use?
They would have to go and alter the K function, because the difference between the CAT and the AM29 was that the CAT only required 2 and it required no manipulation, a 2 cycle, but required no manipulation of the address bus. So it's just moving a value to the data pointer and putting an address in. It's not just a couple of equates. It's really only like 8 lines of code. It's not that hard as long as you read the specifications. Any other questions? Right, next up is Nell Rice.
Good evening. I'm Ronell Rice, and my senior project was an integrated development environment for the 8052. My advisor was Professor Moriarty. For the overview today, I will be discussing my problem statement, my objectives. I will be showing a block diagram of my code, my accomplishments and failures, and future work, and I'll wrap up with conclusions and questions that anyone have. Right now, the 8052 processor is used as part of the solar car project. As a CP, I noticed it was a hassle to have to open up a DOS window to run the assembler, to assemble all the code that we made in like a Word file, and then having to correct the errors, you would have to go back to the .list file and check it out. So I chose, oops, as you can see in the previous assembler, you have to, I don't know if you can see it really well, you have to know some of DOS code and like to find the directory, and you have to know the code to run the assembler, which is just ASM51, then the file name -if. The new way is a lot simpler. It's basically just like opening a file in Word. After the program's run, the IDE is created, and you just have to click on the open file, which brings up the common dialog. After the file is loaded, you click on this icon, which is the assembler, and it assembles, and it'll let you know if you have errors or not. So my objective was to help the students in the solar car by creating an IDE for the 8051 that will launch an assembler and process the errors, meaning it'll let you know what the errors are so you can take care of them right there in the window rather than having to open up the .list file. This is a block diagram of my code. It's fairly simple. A user has to type a file or open a file, and they must save it before it assembles. If there's errors, you can go back and edit right in the window, or else if there's no errors found, it's completed and you can download it to the board. My solution held two mainframes, a parent frame, which consisted of the common dialogue, and it held the child frames. It's the toolbar frame in the back. And then as you open the file, this is a child frame, which consists of just a rich text box and a text box. When it assembles, it launches ASM using a shell command. So it'll pop up and then execute, and then it'll just go away. And the program will automatically go through the .list file, find all of the errors, and report it into the text box, which you can't write in. And it'll tell you what kind of error it is and the line that it was found on. My accomplishments was I successfully launched the ASM51 assembler, and all the errors are found correctly. I also got all of the keywords for the ASM51 architecture to highlight in red. And yeah, all the errors are successfully reported. I failed to get the board to communicate with the with my program. I was not able to. I did not have time to go into like Matt Barker's program to adapt to hyperterminal. Also, for the keywords, it does not yet ignore commented lines. So even if it's comment, like if you just have an and, like writing it out, it'll highlight, which is annoying. And also, I was not able to implement a single-step debugging or break debugger or run to a breakpoint. For future work, if the program is picked up, you could include all the failures, such as editing Matt Barker's program for hyperterminal and adding a single-step debugger, ignoring the commenting lines, and also I wasn't happy with the way the program handles the errors now. It would be easier if you could click on the error and it will jump to the rich text document, the correct line. Right now there's just a line counter at the bottom, so you just have to kind of scroll down. So in conclusion, an IDE was successfully created that launched ASM51, and it highlighted all the keywords. However, it could not communicate with the embedded board. I'd like to thank my advisor, Professor Moriarty, for all of his help and guidance in this program. I'd also like to thank Phil Gorman, who helped me get Visual Basic, and Kevin Gorman for helping debug Visual Basic when it gave me problems. And I'd also like to thank all my peer and faculty members for all their help throughout the years. Are there any questions? Professor Christ?
Is it possible to pull up the entire list file to look at it? Comparing it against the data bus like we did in 360?
I did that. The question was, is it possible to pull up the .list file? The IDE is created just to when the common dialog box is open, it just looks for .ism files. Yeah, otherwise you have to open up in the Word. Yep. Right, I use that to like debug to make sure that it did find the correct errors and stuff. Any other questions? All right, to now present Brian Cox.
Good afternoon. I am Brian Cox. My project is a design of an automatic guitar tuner using a fuzzy logic controller. My advisor is Dr. Ranamai. A brief outline of the presentation. I'll go over the problem statement, the objectives of the project. I'll go over a little of the theory of what fuzzy logic is. I'll talk about the process of how the project developed. I'll go over the final design of the project, the results, and then the conclusions and future work. And I'll answer any questions. Okay, the problem statement. Currently, guitars are tuned manually. This can be very time-consuming and inaccurate, especially in a noisy environment, say like at a concert, where the musician needs to tune up the guitar fast in between songs. It can be very difficult to do. There are tuning devices which aid in manual tuning. These are usually just some form of LED display that when you pluck the string, they'll tell you whether the note is sharp or flat. The tuning is still done manually, however. The idea is to, there's a need for fast and accurate tuning. Fuzzy logic is ideal for this project because it allows for the design to be tuned precisely to how someone might want a guitar to be tuned. The objectives of this project are to develop a fuzzy controller using Simulink, to implement the fuzzy controller using XPC. XPC is a real-time operating system developed by MATLAB. And then to automatically tune the A string of a guitar using this controller. Fuzzy logic is a domain of artificial intelligence. It's based on the experience and expertise of the user. For this project, I asked the help of Chris Ballard to use his expert ear on tuning a guitar. Using fuzzy logic simplifies the complex control systems with and controller design without the need for using mathematical models. It's a non-mathematical approach to solving control systems. This allows the designer to connect the qualitative world to the quantitative world. The process of this project. To begin this project, I needed to learn how to use XPC and how to implement a system in XPC. I had to analyze the signal of a guitar pickup because I've never actually seen what a signal from a guitar note would be. I then had to implement a real-time FFT, and then implement a filter for the signal, and design a fuzzy controller for the overall system. This is the final design of the controller. Over here is the input from the guitar into the capture card for the computer. It then goes down to a filter. This is a low-pass filter which allows just the fundamental frequency of the note to pass through and filters out all the harmonics of the note. It then goes into a buffer. The buffer is needed to find the maximum value later on. So it puts this data into a buffer and sends the array to the FFT. It runs an FFT in the absolute value. This is to do a frequency analysis of the note. I'm then able to find the maximum value, which frequency has the most, to find the strongest frequency of the signal. Because I filtered out all other frequencies, the only frequency that I'll go through is the fundamental frequency and any noise around that note. These switches here are just for protection of the guitar. The first switch here is if the string gets turned too high, then the motor will turn off so the string doesn't break or damage happens to the guitar. The other switch here is actually so if the guitar gets tuned too low, it'll turn off the motor because the harmonics of the note will start to go through the filter and it may try to tune to one of the harmonics. The signal then gets compared to a desired index value. This index value is what was found, is what a tuned A string would be. What it's comparing is what it was found here for an index value in the maximum. The error then goes through the fuzzy controller and then gets outputted back to the motor, where the motor tunes the guitar. These blocks up here